now is the thermochemistry packet. It's the big packet I gave you at the beginning of the year. And I'm going to have you guys turn to page 8. I'm going to start off with the least pleasant of thermochemistry, the stuff that I don't like, no one really likes, but it can appear in understanding type questions. And then I'm going to slide into the stuff that's actually a little more intuitive, like Gibbs free energy and whether a reaction is going to go or not, and bond energies and stuff like that. And that's stuff more in our wheelhouse, along with Q and et cetera. But before we do that, we need to get through some of the unpleasantness. Can I say a quick prayer for us here before we start? And then, yeah. God, I'm grateful for these students that have shown up today, and I know there's so many pulls on our time. I pray that honor their effort right now. I pray allow me to teach clearly and remind them of stuff they already learned, and that ultimately walk out of here feeling as though we accomplished something. In Jesus' name, amen. Okay, so I'm going to turn over to the board here to Mary Catherine. I'm going to be presenting off of her screen, but I want to point out a few of the equations that are the bedrock equations. So we're going to start off with the first one here, and that change in E is the change in internal energy of a system. Now, from here on out, let me redefine for you something that we learned before. And again, it's kind of like with my son, we taught him to take medicine by, we say, medicina para bravos. And that's like, it's kind of like saying, here's medicine for brave boys. And then whenever he takes it, we're like, bravo, bravo. And so we've got him to like get to the point where he's excited about taking this, and he'll take any medicine, which is really helpful, because before we put it in his mouth and he'd be like, bleh, and he'd just spit it out, and that would be the end of it. So this right here, this is medicina para bravos. This is content that none of us really likes, none of us really wants to have to go through, but I'm going to say bravo when we get through it, because this is the cornerstone of some reasoning questions that just screw students up over and over again. So bear with me as we go through this. I'm going to remind you of a few general concepts. First, every single time we're dealing with energy, we're always going to deal with the system and the surroundings. The system is what we care about. Usually that's a reaction of some kind. The surroundings are anything on the outside that impact the system. Internal energy, can you, if you take a look at the equation on the board, change in E is equal to Q plus W. The amount of energy that changes in a system is a combination of both heat and work. Q is the symbol for heat, if you guys don't remember from before. W is the symbol for work. And if you're wondering where we're looking at here, we are on page 8. So other than heat, all energy transferred is defined as work. Now, what we need to understand here is that in thermochemistry, signs matter. Signs indicate direction. So listen to me carefully. We're going to treat every system, reaction, or container we're doing a reaction in as a spoiled child. And simply this, whatever is done to the spoiled child or for the spoiled child, that's a positive. Whatever the spoiled child has to do or loses, that's a negative, even if it's not a good thing for it. For example, if a system loses energy, we would say that that energy change is negative. Would you agree with me? So if I lose heat, if I'm exothermic, my Q would be negative. That's actually really good. We want to lose energy. But it sounds weird because it helps to think of this way, but it's not actually true. Sometimes when we're given something, it's not really good for us. And sometimes when we lose something, it's actually not bad for us. So it's really good for a system to lose Q, to have negative Q. But if heat is given to the system, we have a positive Q. So think of it being given to a spoiled child. They're like, yay, right? It could be like a poisonous snake, but yay, you're giving me something. But it's a bad thing that you're giving me, because no one wants to gain energy. I'm glad we have that as a impromptu example that I just put on there. Poisonous child with a poisonous snake with a child. So can we acknowledge this truth here? Q, when we have an exothermic reaction, is going to be negative. Q, when we have an endothermic reaction, is going to be positive. If we ever heat up a system, give heat to the system, that's going to be a positive Q. Whenever heat is lost from a system, that's going to be a negative Q. Similarly, work done on a system is a positive. Work that a system does on something else, that's a negative. Now, that's going to come into play in just a second, because actually the formula you put on the board there is a little bit off. Can you change where it says work is equal to negative P, change in E? Can you make that the change in V? I was saying so many things at the same rapidly here. So that's the formula for work. And I want to point out something here to you, because they use that formula. And typically when they talk about that formula, they're referring to some sort of piston of some kind that's moving. So can you picture, you guys understand how a piston works? You have a cylinder that's in a container, moves up and down, but that cylinder is three-dimensional. It occupies space, right? So can you do me a favor here? Actually, we don't need to draw it. We don't have time. But if the reaction or something causes the container or something to move out, the volume to get bigger, right? If you look at our formula, isn't work equal to pressure times the change in volume? So if the volume gets bigger, we're going to get a positive V. And wouldn't our work overall be negative? Because we're doing work on the piston or something outside. If, however, our change in V becomes negative. Now, see when we multiply negative by negative, we get a positive. That means that work's being done on our system. So picture, if you would, that let's draw this. Can you draw like a container, just like a cup like this? Here. Yeah, right there. Draw a little container like that, like a picture, if you would, like a bottle. Yep. Okay, and then halfway down, draw like a piston going, like a thing going down and a piston going across. So like draw a piston going across. Yeah. Actually, make it like solid going across, and make it thick. All the way across, even through the middle of that where it comes down. So that is the piston, right? So actually, keep it even like that. Perfect. No, perfect. Okay, now watch. If we have a reaction going on down below, so can you write reaction in that bottom space? Yeah. So we have a reaction. Now that reaction can do one of two things. It can either create pressure that causes that piston to go up, or it can cause it to go down. Would you agree? Are you all with me? I don't know if I think you may be standing right perfectly in front of the drawing, and I don't know how easy it is to see anyway. But now watch for a second here. Would you acknowledge that if you take a look here on, and I'm reading on page 10, the expansion or contraction of a gas against a constant external pressure can be represented by the equation W is equal to negative P change in V, where W represents the work done by or on a system, P represents constant external pressure, and change in V represents the final volume minus the initial volume. The equation will also represent the work done on or by a system when the amount of gas changes due to a chemical reaction, where gaseous substances are produced or consumed. The student will need to know the conversion factor 101.3 joules per liter atmosphere to solve these kinds of problems. We'll get to that in just a little bit. If there's no change in the total volume of gas before and after a reaction occurs, change in V is equal to 0, and there's no work being done. So you understand that work is always essentially is a force over distance or pressure over a volume, over a particular volume. If there's no volume change, no work is done. Our work is 0. Just be aware of that. Note if the reaction is performed in a rigid container, there may be a change in pressure, but if there is no change in volume, the atmosphere outside the container didn't move, and without movement, no work is done on the system. If there's no change in volume, there's no work done on the system, and the change in the internal energy will be only due to the heat. Now, chemicals commonly react at constant external pressure, often at atmospheric pressure. Now, all I want to talk to you about right now is this, and I don't want to go too in depth with this, but will you understand that the piston movement would be your change in V? Right? Pressure is the pressure exerted by the outside on the system. Right? So whatever, right now, aren't we all feeling pressure on us? Equal to approximately 1 atmosphere, right? That would be our P that's acting on us. If the reaction itself causes the piston to go one direction or another, that will determine what our change in volume will be.
That's like when there's like 2 moles of gas on the side, there's 3 moles on the side.
Yep.
We're going to change would be towards more. So
right, because the work is going to be involved, which occupies more volume, which occupies less volume. We're going to get to that in just a second when we do some practice examples here. Now, let me point out 2 other things for you here. That equation up above, we've talked about change in enthalpy a bunch before. Change in enthalpy, I've actually said is the products enthalpies minus the reactants enthalpies. And what are enthalpies? It's the amount of energy essentially in the bonds of something. Well, there's another way we can write this equation. I don't want to get into great depth on this, but the change in enthalpy is also equal to the change of energy plus work, and work's formula is P change in V. Now, if you have a constant pressure, that equation gets removed down to change in H equals Q, and I want you to pay really close attention to that. Write that down somewhere in your notes. Change in H equals Q at constant pressure. Why? Because what they've often done in problems is they're talking about enthalpy, and all of a sudden it becomes a heat problem, and students don't know how to correlate between enthalpy and heat. Enthalpy is equal to heat, when there's a constant pressure. And can I remind you, can you right over to the left-hand side or right-hand side? Maybe I have to move you might have to move your laptop maybe to the middle of the table. This is kind of getting hard to see. They move it like right to the middle of, yeah. Do you guys remember the formula for heat? I'd be kind of impressed if you do. For heat. Okay, Q equals MCAT. You guys remember Q equals MCAT? So can you write somewhere down there, write Q equals MC change in T? Q. Baby Q. Baby Q is what we use for heat all the time. Q is equal to MC and then change in capital T. And it's baby M, baby C, change in capital T. By the way, we got a brand new packet of pens on the table. It would not be a bad idea to use one of them. So watch. See that formula right there? We're going to talk about this a little bit later in class, but that Q there stands for heat lost or heat gained, and we can actually solve for heat lost or heat gained by knowing the mass of something, the specific heat of something, and the change in temperature. But the correlation, see how the change in H equals Q? That allows us to go between an enthalpy problem and a heat problem. Just be aware of that. If you ever have a problem, they're talking about enthalpy and or whatever, and then all of a sudden it becomes a Q problem. That's because we're at constant pressure and those two variables are the same. Can you just lock that into your brain that at constant pressure, enthalpy is the same as the heat changed? Are you with me? Because we're going to spend a lot of time today in class going through heat. Now, let's take a look at the problems that are on page 11 and actually 12. If you look at the sample problem at the bottom of page 11, can you maybe hold your thing in front of the screen? And it says a gas absorbs 28.5 joules of heat and then performs 52.2 joules of work. Now, really quickly, if a gas absorbs 28.5 joules of heat, what's the sign of our heat? Positive, right? Because we're absorbing heat, right? And if it performs 15.2 joules of work, what is that sign? Negative. So if we wanted to figure out the overall change in energy for that particular system, wouldn't it be adding these two together? As long as you know what the signs are, we're going to be okay. True story? And if you add them together, I'm sorry? It absorbs it. Absorbing means that he is getting, it's an endothermic reaction, it's coming in, and that means that, think of a spoiled child. If you're giving me something, even if it's not good for me, if you're giving it to me, that's a positive. So that'd be positive Q. And then I'm having to do work. So because I'm having to do something instead of something being done to me, that's a negative. So we have negative W. Now, flip the page, and here's where it gets a little bit tricky, and I want to remind you of the formulas we have on the board so you guys can solve for it. Now, if you take a look at can you write H2OG? H2O as a gas goes to H2O as a liquid, please. You can erase that middle little diagram if you want. H2O gas goes to H2O liquid. Now, if I told you that reaction was exothermic, could you tell me what the signs for Q and W are? Well, let's start with Q. It's exothermic. It's negative, right? So we could say negative Q, right? But then work. And the question is, what's happening in this reaction? And let's specifically think about volume, because if you take a look at the formula, isn't work equal to the negative pressure times the change in volume? Are you all with me on this? Now, they gave us a standard pressure, didn't they, of 1 atmosphere in the problem itself. Now, let me ask you, in that formula, what's happening to the volume when you go from a gas to a liquid? It gets negative, right? So if it gets negative, what's going to be the sign for our work? Are you with me? Yeah. So we can look at the states of matter and kind of determine what the W is. So, and the base equation that we're dealing with here is that equation right there. So let's look at another one here. Let's look down at number 7. And 7A. And they give us Sn, can you write Sn solid? Sn solid plus 2F2 gas goes to SnF4 solid. So let's take a look here. And remember, when we're talking about work being done, in particular when we're dealing with, states of matter are going to matter here because the volume is really what we're looking at here. Do you see how we're going from 2 moles of a gas and 1 mole of a solid to 1 mole of a solid? What's happening to my change in volume? It's going to become negative, right? When we have a negative change in volume. Now look at our equation. If we have a negative change in volume times a negative pressure, wouldn't that give us a positive work? So that'd be a positive work. Let's look at, right now, can you just hold the example in front of the book? Because I don't want to spend a ton of time with this. Can you hold the example for B? So everyone look at B. AgNO3 aqueous plus NaCl aqueous goes to AgCl solid plus NaNO3 aqueous. And the question is, what work is done? Actually, no. Because here's the thing. The only time that you have a change in, no, watch. If we were talking about entropy, absolutely, there's a difference between solid, liquid, and a gas. You all agree? In the next step, when we talk about entropy, change in S, then that's going to matter. But in terms of volume, do you realize a liquid has a constant volume just like a solid has a constant volume? You guys realize that, right? So if I have this container filled with water, this little bit of water, that amount of water, this is so pathetic, but that amount of little water that I have right here, that occupies the same amount of volume no matter what, right? Same as a solid occupies a certain amount of volume. So if we're comparing volumes from the left-hand side, essentially we have AgNO3 is aqueous. Wouldn't that be a constant volume thing? NaCl is aqueous, constant volume thing. AgCl is solid, constant volume thing. NaNO3 is aqueous, constant volume. So if there's no change in volume, we have no work done. Wouldn't our change in volume be 0? Are you all with me? Now they do the same thing if you look at C. They go from 1 mole of a gas to 1 mole of a gas, and actually go from 1 mole of a gas in a solid to 1 mole of a gas. Do you realize if you're going from 1 mole of a gas to 1 mole of a gas, it's essentially negligible, the volume change? And then lastly, let's look at the very, very last one here. You have a gas on the left-hand side, and then you have 2 moles of gas and a solid on the right-hand side. Would you agree with me that we're going from a smaller amount of gas to a larger amount of gas? So what's happened to our volume? Volume's increasing. If our volume increases, what happens to our work? Work positive or negative? Where it's going to be negative. So in this case, work is being done on the system.
So if we know,
I'm sorry, that work is doing, the system is doing work because it's negative work. Wow, it's hard.
so if it's constant volume, then we know that work is going to be 0. So.
Absolutely.
And then, oh no, it'll just equal. Okay, you're right.
Right, and then energy.
Multiplied by.
No, and so by the way, look at the let's backtrack here. Can you put your finger on the change in E equals Q plus W equation? I don't know if you can see. Yeah, so we can see that. Everyone look at that equation. That's the change in energy in a particular system, right? So if my work is nothing, wouldn't my change in energy just be due to my heat? So if we have no volume change, then all of our energy change is due to the heat. And that's usually whether a reaction is exothermic or endothermic. So that kind of ends the lame portion of the lecture. Now we start getting into the good stuff. Okay. So what I'm going to do right now is I want you guys, we're going to go a couple ways here. What's that?
You promised a bravo.
Bravo! So you are like my child. That is good to know. So let me talk to you about a couple things you guys probably already know. And maybe we can do a little bit of erasing here. And can you write for me? Yeah, let's erase everything. Okay, can you guys all turn to the bottom of page 27? And would you mind writing the equation? It's the very bottom of page 27. The change in enthalpy of a reaction is equal to change in the sum of the N change in F products. Bottom of page 27. We'll talk about that right now. And that, in essence, is why we're having this help session. Make sure we understand the difference there. Can you write that at the change in enthalpy? Make sure the knots are really important because knots mean what? Standard conditions. Now, it also means initial if we're dealing with, remember how we're dealing with concentrations, that also means initial. But in terms of these problems right here, we're referring to standard conditions, and that's a big deal. Okay, now what can you write for? Can you write Rxn for next to the change in enthalpy with a 0? Change in enthalpy, not the first one up there. Can you write Rxn as the subscript to the right of it? Yeah. All right, let's pause for just a minute. So every single compound that is formed, it had an enthalpy of formation. That is the amount of energy that was either released or gained when that compound was formed from its atoms. Now, can you guys bear with me on this? Would you acknowledge that if my atoms are by themselves, they are not very stable, but when they become a compound, they lose energy and they become stable, right? That amount of energy that's lost to form that compound, that's called the enthalpy of formation for that compound. An example of this would be, could you write C solid plus O2 gas goes to CO2. And can you write change in H naught F equals negative 394 kilojoules per mole. Okay, now I'm being deliberate right now because I want to emphasize something. Enthalpy of formation is always per 1 mole of that thing. So do you see how on the right-hand side we have 1 mole in front of, or 1 in front of the CO2? So the enthalpy of formation is when you take elements, can you put your finger on the C? Isn't that C an element? Isn't O2 an element? It's the elemental form of oxygen, right? So, and then CO2 is the compound. When we form 1 mole of a compound from its elemental form, we end up with the enthalpy of formation for that thing. Now, write this right underneath it. Could you write 2H2 plus O2 gas, so it's both of them are gases, yields 2H2O liquid. The change in enthalpy of that is negative 572 kilojoules per mole. By the way, the per mole, do you realize they love to go times mole and -1? Like that's their favorite thing to do. So we really don't care how we do it. Now, here's the problem with this. Is that truly an enthalpy of formation? Why not? It's per 2 moles. So that's really an enthalpy for the reaction. So if we wanted to actually figure out the enthalpy of formation for water, wouldn't we have to divide everything by 2, including the enthalpy of formation? So enthalpy of formation would really be, wouldn't it be H2 plus 1/2 O2 goes to H2O. Now, here's the thing. People hate having a half of an oxygen. So they write this as the enthalpy of formation equation, realizing that in your heads, if you ever needed to figure what the enthalpy of formation for water is, you have to divide it by 2.
How do you have half and O2?
You can't. But that, if you're doing the true enthalpy of formation for 1 mole of a compound, you'd have to end up having a. That's why they write it like this, and then in the end you have to divide by 2 to get the enthalpy of formation. Now, why did I just share this with you? Because every single compound that's formed has an enthalpy of formation. Those enthalpies of formation, they are found in tables. And we have a table in the back of our book that lists all the changes of enthalpy, and all of them are always in kilojoules per mole. Remember I talked to you about this. Now, why is that a big deal? Well, if we have an entire formula, we can look at a table. Are you all with me? We can look at a table and then use the equation up above. Can you put your finger on the equation up above there? Changing the enthalpy of a reaction is the sum of all the enthalpies of formation of the products minus the sum of all the enthalpies of formation of the reactants. So let's take an example here, and let's go.
Genius.
Can you write CH4 to the right-hand side here? Let's look at an equation, and I just want to remind you how we figure out the enthalpy of the reaction. Right, CH4 gas plus 2O2 gas goes to CO2 gas plus 2H2O liquid. Now, can you write change in enthalpy for the reaction equals enthalpy H naught Rxn is equal to, now let me walk through this with you. It was messing around earlier, by the way. Okay. Now watch. Would you all acknowledge that we have 1 mole of CO2 and 1 mole of H2O on the product side? So we can look up on tables, and they'll typically will give you a little chart that tells you the enthalpies of formation of everything on here. Understand this, that states of matter we want to focus on. And in this particular case right here, wouldn't we go, wouldn't the products be CO2 and H2O? So what we could do is we could write, wouldn't it be 1 mole or 1 times the, now here's where I have to give you numbers here. So would you be okay? Let's just write this out so we know what we're doing. Could you write is equal to 1 times the change in HF and put as a subscript down below CO2. HF and then CO2.
We not use the
Plus,
liquids.
what's that?
We don't use the liquids. They don't count.
Oh, we absolutely do. Plus, and there should be a 2 in front of the H2O, by the way. H2O on the right-hand side of the equation. Yeah, 2 right there. That's all right. So and then we're going to have plus 2 times the change in HF formation of H2O liquid. And can you put a big parenthesis around those, like a big square brackets? Yeah. And we're going to subtract from that 1 times the enthalpy of formation of CH4 plus 2 times the enthalpy of formation of O2. And put a square parenthesis around that. Okay, now let me remind you of a couple things really quickly. Go ahead, Luke.
So in this equation, you multiply the entropy or enthalpy of the water back to.
Right. So watch. Or we actually know what it is for times 2, right? So we wouldn't have, like in this case here, if we were looking at a table for water would have the enthalpy of formation as half of what we had over there. It would actually be written as negative 286.
Oh, with the reaction here, like that?
But if they gave you the reaction like that, then it already is for 2 moles of H2O. So you would just take that number right there and plug it into for the 2 H2O.
So on the table, what it say 1 H2O?
Yeah, all of them are for 1. That's what I'm saying. That's why I paused it. So on the table itself, they're not doing all the reactions. That's we sometimes will end up with an equation. So the equation on the board, the 2 H2O plus O2, that's actually the equation they attribute as the enthalpy of formation of water. However, when you put it into a table, it's always per 1 mole. So if you have a table, they'll give you the heat of formation of water per 1 mole and it'll be negative 286. But because there's a 2 in front of it, it'd be the same as the actual equation. Does that kind of make sense? Now, I am not going to plug the numbers in, but if they give you a problem like this, you put your finger on the heat of enthalpy of formation of CO2, right there, right there. There will be a number that you will be able to get from a table that we put in there, and we'll have to multiply it by 1, right? Then put your finger on the H2O. In this case here, it would be 2 times the negative 286, right? Put your finger on the enthalpy of formation for CH4. Now, in that case, again, we'd look up on the table and we'd actually have a change in H for that particular thing. Are you with me? Take a look at O2, though. You realize that the heat of formation of an element is 0?
Yes, I remember that.
You guys remember this here? So in this particular case, and this is, you guys note somewhere, enthalpy of formation for an element is 0, or any diatomic element is 0. And it's one of the things that sometimes stumps students because they're doing a problem and they get all the enthalpy information and then they're like, wait, there's no enthalpy information for O2. How can I solve this problem? That's because the enthalpy information of O2, N2, H2, Cl2, F2, all of those that are halogens or diatomic is 0. Can I get a head bob around the room? That is an incredibly important piece of information to pack in. So this is the main way that we're going to figure out enthalpies of formation. I'm sorry, enthalpies of a reaction. Why is that important? Because whether or not a reaction loses energy or gains energy determines whether or not it is thermodynamically favorable. Would you all acknowledge that every reaction, if it has a dream, wants to be an exothermic reaction? Are you all with me on that? Which means that every single reaction wants to be a negative change in enthalpy for the reaction. Are you all with me on that? True story? There's a second way to solve this, and it's with bond energies. So, can you write this formula down? And let's flip over to page 29, please. And can you write right underneath the equation that you wrote above? See where you wrote the change in to the far left. Can you write in a different color pen right underneath that? Change in enthalpy for a reaction, the same exact change in enthalpy not. So there's two ways we can figure out change in enthalpy. Use like a brand new pen for underneath there. Like the purple or the blue, they show up really, really well.
The purple is already missing.
Oh, come on, man.
That's what I was saying.
How's that? How could that happen that quick? Try this one here, the pink. Oh, then use that one. Do you mind if I just toss it to you because this is a good pen?
What the heck?
Close. Okay. All right. Underneath the change in enthalpy of the reaction, can you write change in enthalpy of the reaction again, but this is a different color. Up above, right? Like literally right underneath it. Do you mind? With the rub underneath the one you did up above. Yeah, perfect. So I want you to mirror these two. You're doing fine. Stop it.
Oh.
Equals. He said nothing. Can you do the sum? Can you do the? Can you do the same the sum of thing? But just write the sum of, and then write n bonds broken. Like write the words bonds n times bonds broken.
Trying to write a word.
Minus. You can maybe put n time as put the parentheses around bonds broken. One minus the sum of n times the bonds formed. Okay, listen carefully on this because you know with me. So every time we do a change of a reaction, change of something. It's always products minus reactants, products minus reactants, products minus reactants. Are you okay with that idea? If I ask you for the change in entropy for a reaction, it's the entropy of the products minus the entropy of the reactants. If I ask you for the change in enthalpy of the products minus the enthalpy, listen to this even. If I ask you for the change in Gibbs free energy for a reaction, we can actually do that. We can actually do the Gibbs free energy for every single compound. It's the Gibbs free energy of the products minus the Gibbs free energy of the reactants. The only exception to that is when we deal with bonds being broken and formed. And here's the thing. In order for a reaction to occur, mustn't you break all the bonds first in order to be able to form them second? So what they're going to do in a problem like this is they will give you a table that shows you every single bond energy of every single thing you have to break apart. So let's take a look at the CH4, the equation up above. So can you put a little arrow from the CH4 in the actual equation we have to the right-hand side, put a little arrow down. Like a little loopy arrow, like there, yep, and it's right there. Would you acknowledge that if I were to draw that structure, can you make a C with 4 H's around it? Brilliant. So would you acknowledge that there are 4 CH bonds there? Didn't you write 4 times CH? Okay, C dash H, right? Plus, don't we have 2 oxygens? But each oxygen, isn't it an O double bonded to another O? So what we'd have is we'd have 2 times an O double bond to an O. Why is that a big deal? Because if we want to break those bonds, that's going to require a certain amount of energy. It's not, we don't have a bond energy of 0 for O2. Does that make sense? So what we have in a table, and if you take a look here, we're going to add up all the bonds that are broken, and then from that, we're going to subtract all the bonds that are being formed. And we're going to get these values straight from tables. So can you pause for just a second here? I think you've already gone ahead and done. Great. So we had how many? We had one. So put a big parenthesis. Yeah, that's perfect. Can you put a big parentheses around the new stuff we're going to do? Subtract, big bracket, and then we have 2 times.
Well, it's 1, 2.
Right. So 2 C double bond O's, right? And then plus for water, don't we have? It's H2O, right? You kind of went to be honest. Oh, in the middle, 2 H's.
It's 4.
Oh, in the middle, 2 H's. So would you agree with me? For every one water, aren't there 2 OHs?
Oh, yeah.
So when we go 2 times 2 OHs, which, if I'm not mistaken, isn't that 4 OHs? Now, what you're going to have on a table, you're going to have a bond energy table. And can you do me a favor here? Can you put your finger on the CH in the original, right there? And make sure the camera can see you're kind of in the front of the camera. Maybe move the camera to the middle. On a data table, on a bond energy table, they will actually have a bond energy for CH. They also have a bond energy for O double bond to an O. They'll also have a double for a C double bond to an O, et cetera, et cetera. So you'll be able to look down the table and you'll be able to find the bond energy for every single bond that we're working with. Are you with me? Now, I'm not going to plug the numbers in this case here. But could you write on the outside of that, could you write change in H reaction equals, so change in H naught, RXN equals that. Do you realize that if we did, can you go to the, can you put your finger right above it with the enthalpy of formation in red? Up, right there in red. So, yeah, to the right. See how we did the equation for the change in enthalpy for the reaction when we used enthalpies of formation and we went the products minus the reactants and solved it out? Put your finger down on the blue one. For the change in enthalpy reactant when we're dealing with bonds, bonds broken minus bonds formed, do you realize that we'll get exactly the same change in enthalpy for the reaction in both cases? The bond, if I break all the bonds and then I form the new bonds and I add and I subtract the two from each other, the change in enthalpy for the reaction will be the exact same thing as if I took the products, enthalpies of formation minus the reactant. So if you take a look at those two equations in red and blue in the upper left-hand corner, both of those will give you the exact same number. So what they sometimes will do is they'll give you a problem and they'll start you out with bond energies. But then it'll morph into a Gibbs free energy problem. Well, how could that do that? Well, first of all, you realize that change in enthalpy is essentially the amount of energy that's gained or lost in the reaction, right? Yes, yes, sir.
So in this reaction, O2 bonded to does.
Yeah. So bonds themselves have energy. So if you look at O2, right? In order to make O2 become CO2 and H2O, mustn't we break the O2s apart so that now the O's can bond with other things? So it requires energy to break them apart. The amount of energy to form them is zero because they exist as O2. So it's like this. If I have O2 and it's just floating around, right? It exists as O2. But it didn't require any energy to be gained or lost to form this because this is how I exist. But if I want to break those apart, I'm going to supply a certain amount of energy, which we call a bond energy, to break them. So now those O's can easily go and attach with a carbon or a hydrogen on the other side.
On the bonds form side, you don't put it as a value? Is that
Oh, we put it at all times. So when we're breaking or forming bonds, it requires a certain amount of energy. What we're talking about in terms of formation, literally think about this. Do we have to form O2? That's how it exists as an element. Do we have to form carbon? No. Do we have to form, God put into place, we have carbon all the time. We have oxygen all the time. We have nitrogen all the time. N2, O2, Cl2, that's how they exist. their formation enthalpy is 0 because they require no energy to form them. But if I want to break their bonds or then reform them into something else, I've got to put energy in to break those bonds apart. You guys follow me here? So that's the difference. Don't you dare put like bond energy of 0 for O2 because you have to actually break the bonds. Now, here's where it gets good. So can you do me a favor here? Can you, does everyone feel okay with what we've done here on the board? I want you to pay particular attention to the 2 different ways we can figure out enthalpies of a reaction. Because you may see either of those 2 ways of a problem solved. Can we erase everything except for those 2 things in the upper left-hand corner? And let's talk about Gibbs for energy and how reactions go. Whether a reaction is spontaneous. How are you guys holding up here? You guys doing okay? Okay. Now, here's where I'm going to actually flip over to the Bluffer's Guide. So can you turn to the Bluffer's Guide because it has some pretty cool, I think it's really helpful. Can you show everyone that's at home the actual, literally the first page of the Bluffer's Guide. Just show them that packet. It's over there if you don't have it. Okay, so I'm going to go a little bit more and fast forward on this here because I'm assuming you guys, yes ma'am. I'm assuming you guys understand this stuff a little bit better. So that's the packet we're on right here. So there are 2 things that determine whether or not a reaction is spontaneous. Now, instead of using the word spontaneous from here on out, the chemistry overlords, they decided that spontaneous scared students, so they are going to use the term thermodynamically favorable or thermodynamically unfavorable. What that simply means is this: if a reaction is thermodynamically favorable, it will go. If a reaction is thermodynamically unfavorable, it will not go. So there are 2 things that determine whether or not a reaction is thermodynamically favorable. One is what we've just been talking about, change in enthalpy. When we think of change in enthalpy as essentially energy changes. The other thing that causes a reaction to go or not go is entropy. Can you write change in S naught on the board, please? I beg your pardon? No, but yeah, why not? Write the Gibbs energy equation. Right, change in G naught is equal to change in H naught minus T change in S. Oh,
Cookies were so good.
I never had one.
Ethan had, Luke had 5.
I have 5.
Blue.
Sure.
Now, can you underline change in H with a different color pen and change in S, and can you make sure you have a not symbol by S as well? Now, as we're going through this, I'm gonna make the assumption that I know is kind of tricky that you guys have a basic understanding of this. So let me just kind of run through this. Entropy is disorder. Everything in our universe tends towards disorder. So reactions, it's easy to be disordered, so they want to have disorder. Are you with me? So in a perfect utopian world, if you talk to a reaction and said, what do you want? They'd say, 1, I want to be exothermic, and 2, I want to have more disorder. Would you agree with me on that? Another way of saying that is the best possible thing for a reaction is to have a negative enthalpy change and a positive entropy change. Now, are you with me right now? So if I offer you, and I'm going to use the word good and bad, never ever in an answer for a grader talk about it's a good enthalpy or it's a bad entropy. There's no such thing. If you want to say it, you could say the change in enthalpy is thermodynamically favorable or it's thermodynamically unfavorable. If I have a positive enthalpy change, is that thermodynamically favorable or unfavorable? Positive enthalpy. That's unfavorable because I'm gaining energy and I don't want to gain energy, right? If I have a negative change in entropy, favorable, not favorable? Not favorable. So if I have both of those conditions, do you realize that no reaction will go at any time? Yes. Now, here's where AP graders love these questions, and you probably will see it on, I mean, you absolutely will see a question like this. Whether it's on a multiple choice or whether it's on a longer answer, that depends, but every year they have questions on this. The question arises, what if we have one good condition and one bad condition? Talk with me. I allowed you a break here. So can you do me a favor here? Can you circle T? So here's where I want to, and you guys probably know where I'm going with this, right?
Yes.
Change in H has no variable attached to it. Change in S has temperature attached to it, which means that the size of T will impact our change in S expression. In fact, our T change in S expression is a combined expression. Now, if we follow this, let me remind you that a reaction is spontaneous or thermodynamically favorable when change in G is negative. So somewhere in your notes, just remind yourself, we want a negative change in G, a negative Gibbs free energy for a reaction to be spontaneous. I have no idea. Because Gibbs probably was the guy who was working with it. Now, so follow. If you're a mathophile, this is going to become really easy to you because you see how the negative, we're subtracting the second expression, right? So think of this way. Put your finger on the change in H for me, please. And you're going to have to slide the camera over a little bit because it's not recording the right now. Thank you for that. Okay, watch. If our change in H is not favorable, do you realize that we have to subtract our T change in S expression from that? So now watch this. If our change in H expression is not favorable and our S expression is favorable, under what conditions of temperature will the reaction go? He's right, but I want you guys all to reason. Let's say that our change in enthalpy, let's write our change in enthalpy is positive, and our change in entropy is positive as well. Okay, so in one case, the positive change in enthalpy is no good, right? Positive change in entropy is good. So what they'll say is, under what conditions will this reaction be thermodynamically favorable? And you would say, as the temperature increases, the reaction becomes more thermodynamically favorable.
This one is, which one's the versus?
That's entropy. And that's enthalpy.
And you want this to be.
You want that to be negative. You want to lose, so enthalpy is energy. We want to lose energy and we want to gain disorder. So we want to have negative enthalpy and positive entropy if at all possible.
So if entropy is the thing that's increased and the other one's the thing that, and the enthalpy is also increased, then we want to outweigh the bad increase of
With enthalpy with the
entropy gradient.
absolutely.
And then also if the entropy is diminished and the other is also diminished, then we lower the temperature.
No,
Get rid of, no, I switched it.
yeah. So watch. Let me suggest this way. First of all, do you realize that temperature in these cases has to be in Kelvin? If you yeah, and Cody, repeat that again. Yeah, if you have a Celsius temperature, that would just mess us up because couldn't you have a negative temperature? And then all of a sudden now you're changing the signs. So let me do a couple of scenarios here, and you're just going to tell me under what conditions a reaction will go or will it not go. And we're going to use the term thermodynamically favorable, okay? Let's say we have an exothermic reaction. So you're jumping already. Inside. Exothermic reaction and more disorder. Under what conditions will it go? All conditions. If we have an exothermic reaction, which, by the way, what does exothermic mean then? Change in enthalpy is?
Negative.
If I have an exothermic reaction, I'm losing energy, right? So, and that's good. We have a negative change in enthalpy. So let's say I have a negative change in enthalpy, and I have less disorder. So we want to have lower temperatures so that the S doesn't impact us as well.
Why is it all?
I'll give you 1 second. Yeah, you're first.
Is it greater endothermic and then greater disorder.
Okay, so when we're saying greater, we're simply talking about positive or negative, right? So if I have a negative enthalpy change, that means I'm exothermic. That's good, right?
I'm exothermic.
Which means you have a negative change in H, which is really good. Okay. Okay. And if I had entropy, entropy is my S. If my change in S is negative, that's bad because I'm losing energy, right? So the question is, under what were you saying which one was both good and always?
Yeah.
Okay, so make the change in entropy positive. The change in entropy is positive, then that's also good because we want to have more disorder. Make 2 check marks next to that. Under what conditions will that reaction go? Well, both conditions are good. Under every condition that reaction goes. That's why they said under all.
This is what you want.
Absolutely. That's the perfect scenario right there. That's both conditions being great for us. But if one condition is good or thermodynamically favorable, and another one's not, then temperature determines which one becomes more important to us. And occasionally, if our enthalpy is good and our entropy is bad, we want to make the entropy smaller.
What if it's endothermic?
Okay, endothermic. Let's say it's endothermic. Let's do that scenario. If it's endothermic and we have more disorder. So endothermic means we have a positive change in enthalpy. Is that good or bad? If it's endothermic,
unfavorable.
that's unfavorable, right? And we have a positive entropy. Is that favorable?
Yes.
That's favorable. So if we have, are you with me right now, Mary Catherine? Our change in H is bad. Our change in S is good.
Wait, which way is it?
If I have a positive change in enthalpy, that means I'm gaining energy. Is gaining energy ever good? No. Okay. And I have a positive enthalpy change, that's good. So in this case, we have one good and one bad. That's where temperature comes in. Now the question is it entropy that's good or is it enthalpy that's good? And in this case, isn't entropy good? So we want to jack the temperature up. That makes sense? Okay. Now your question was, which variable do they give us in joules and which one they give us in kilojoules? So I'm doing this right now. We're doing just qualitative analysis, right? We're not plugging numbers in. And these are the type of questions we're going to get. But they could actually give us enthalpies of formation. They could actually give us the change in H. They could actually give us the change in S. And they could actually give us the temperature. And we could actually plug those numbers in and solve for Gibbs free energy. Here's the problem. If we have a table, changes in enthalpy are always in kilojoules per mole. Entropy, S, is always in joules per mole. Do you see how we're subtracting one thing that is in joules and another thing is in kilojoules? So you must convert either the joules to kilojoules or the kilojoules to joules to be able to subtract the two from each other, or else your math will be completely off.
Is there any way to figure out in this table?
We can figure out the sign of entropy, not what the actual value is.
Okay. So they just have to change of entropy here.
Yep. Now, can I point out something here to you? They could actually, this is what they could actually do. Couldn't they give us a table for enthalpies of formation and give us a reaction and we could solve, can you do me a favor here, Mary Catherine? Can you put your finger on the upper equation? Okay, that upper equation, couldn't we, if they gave us enthalpies of formation for an entire reaction, like we did in the previous problem, couldn't we figure out the enthalpy of the reaction?
Yeah.
And then if they gave us a table that had entropies, couldn't we figure out the entropy for the reaction by doing the same exact formula? Couldn't we, instead of change in H, couldn't we write change in S in that same spot and do all the entropies? But the entropies are going to be in joules. So we have to convert that to kilojoules, plug them in there, multiply it by Kelvin to get our Gibbs free energy. By the way, you could also have Gibbs free energy equation like that. Change in G is equal to the change in G of the products minus the reactants. Now, are you with me so far? Let me give you one more scenario before we move on. Can you write this equation down? Could you write Two H2O Actually, I don't want to do that one. Let's erase that one, sorry. Let's go NH4, CO2, NH2 solid. It's a really long compound. NH4, CO2, NH2 solid goes to 2 NH3 gas plus CO2 gas. And the change in enthalpy of the reaction, so right, change in H for the reaction is plus 159.2 kilojoules. It's not on there. It's coming up with a new one. Okay, here's my question to you. Under what conditions, if any, is this reaction thermodynamically favorable? So let's take a look first at the most obvious. Let's always start with the enthalpy. Is that enthalpy favorable or not favorable? Not favorable because it's positive, right? So then the question is going to be, is the entropy favorable? So how do we know that the entropy is favorable? Okay, so now let me be really clear. Here's how we have to explain it. Okay, you can't just say there's more moles. You have to say because there's 1 mole of solid on the left and she's blocking my view, so I can't really see, and there's 3 moles of gas on the right, the change in entropy is positive. So what you'd say is this: if the change in enthalpy is unfavorable and the change in entropy is favorable, under what conditions will this reaction go? Under high temperatures, because entropy is good, right? Are you with me? So I want to point out here, if they ever give you a reaction, let's remind ourselves, gases are way more disordered than liquids, are way more disordered than solids. In fact, 1 mole of gas, it doesn't matter how many moles of solid or liquid you have, that 1 mole of gas is going to have more disorder than any number. Gas, liquid, solid. And liquid and aqueous are kind of hand in hand.
It's not this.
No.
It's just, if this was
Now, it would be if that was a gas.
but just because of the presence of solids here, you know that this is a negative.
It's a constant.
Positive entropy, because gases are more disordered. We want more disorder. So if we start off,
So what if there's more gas on this side?
okay, well then that'd be negative disorder. Then that'd be bad. So watch. Let's do the 2 scenarios here. So let me walk through it. So right now, let's look at this scenario here, gentlemen. Do you see how we're starting with a solid on the left-hand side in this equation?
Yes.
And then we're becoming a gas.
Yeah.
In fact, not only becoming 1 gas, we're becoming 3 gases. 3 moles of gas. So if we go from 1 mole of solid to 3 moles of gas, clearly our disorder is becoming greater because moles of gas are way, way more than. So let's pretend though, let's change the S on the right to a G, and let's put a, this is not accurate clearly, and let's put a 5 in front of the NH. What the heck not? Why the heck not? 5 moles of gas on the left, 3 moles of gas on the right. What would the entropy change be in this case? 5 moles on the left, 3 moles on the right. Wouldn't we have a negative entropy change? Is a negative entropy change good? No, that's bad. So under what conditions will this reaction go? None, because we have a bad enthalpy, and now we have a bad entropy. The reaction has no shot of going. Does that make sense?
Okay, so what if this was
I
just,
Go ahead.
if this was like 1 solid and this was 1 gas, it'd
Oh,
still be
gas wins by a ton. In fact, put the number 4 in front of the solid. Let's say we had 4 moles of solid, right? And we had 1 mole of gas. 1 mole of gas wins.
When does the solid not win? Or when does the solid win?
Never.
Okay.
Solid only wins if you have on the other side also a solid.
It'd be like playing paper. And
So you can only get solid only
So
wins.
if I had 4 of this plus 1 solid here, solid would win. and the-
No, because you still have a gas.
Oh.
If you have a gas anyway, now solid wins on that side.
Solid wins. Are you kidding?
Does that make sense?
Yeah.
More moles of gas, more moles of anything wins against less moles of anything in terms of disorder.
It's just like one kind versus
More moles of one kind versus less moles of that same kind wins. So more moles of solid wins over less moles of solid. 1 mole of gas will win over any number of moles of liquid or solid underneath it.
So the gas winning on the right side is going to
More disorder. And your positive entropy, which we love. Yeah? So what they could do in a problem, and they love doing this now. I know that you guys have gotten this, so I'm going to close this end up and we're going to move a little bit forward with, and then we're going to practice problems. Every single time they give us a problem and they just give us an equation, we automatically should know qualitatively whether or not the entropy is positive or negative. We won't know the numbers unless we actually have an entropy table. Are you guys with me? They could give us, if they give us an entropy table, then we plug the entropies in, products minus reactants, and we'll actually get the entropy, but make sure that we change from joules to kilojoules. True story? Now, let's move on to the packet here. And if you want to look through this here, they kind of walk you through, if you look through 1 through 6, I want to focus on 6 right now. Mary Catherine, I understand, but man, you should have more urgency than everyone. Everyone look at number 6. Can you show number 6 on the screen?
on the same little 20.
Number 20.
Nobody know I have a brother.
You have a brother?
What? Wait. No,
How
I'm not
is
saying
that?
that sarcastic. I didn't know.
Are you being
I knew
serious?
you had a sister.
How old is he?
Brother.
Are you actually being
The first page. The first page. 6.
I knew you had a sister.
Yeah, I didn't know.
That kind of froze. Can you put it back up there again?
You have a brother?
Okay. Hey, stay with me here. Another 5-10 minutes, and we're going to close up this party. And then this is actually probably the most important stuff because it's stuff we've probably trafficked in the least.
Yeah.
So there is a relationship between K, change in G, and E. Let's raise everything.
Is this K Kelvin or K?
That's K equilibrium. So right now, if you take a look at 6, we have the big 3, and this is the reason why you wanted to be here today. Because one of the hardest things is when we have to move from one of the major 3 to another. So K is equilibrium, agree? G is thermochemistry, E is electrochemistry. So we're going to walk through some formulas here that relate all these to each other. Okay, so let's flip the page. And if you're wondering here, there's a few equations, and if you take a look, can you show the second page? And I want you to focus on change in G equals change in G naught plus RT natural log of K. The second page. Can you turn the page and just show
Oh,
the
it's this equation.
Which example?
literally just the top of the page.
I always forget this equation exists.
Okay, so first things first. See where her finger is right now? Keep it right there on the equation. See that equation where it says change in G equals the sum of the change in G of products minus the sum of the change in G of reactants? Isn't that exactly the same formula as our enthalpy reaction formula? So guess what? They could actually give us a change in G table, and we could solve using that. However, what often happens is we deal with not standard conditions reactions. It's very rare for reaction to be under perfect conditions. So that means our change in G will not be with a little naught. It'll actually be a regular change in G. Now, if that happens, that means we're not under standard conditions. And you see on the next formula here, change in G equals change in G naught plus RT natural log of Q. That Q is the same Q that we worried about with the Nernst equation. You guys remember that? The same Q. So in this equation, I want to point out a couple things here. Do you see how it says that R is 8.314 joules per mole Kelvin? That's the gas constant we use in this case. Temperature is the Kelvin temperature, and Q is the reaction quotient. Now, really quickly, if the concentrations of reactants and products are all 1, so if we're at standard conditions, can you write that equation on the board, please? Can you write change in G equals change in G naught?
Standard condition is 25 Celsius, 50 Celsius.
25. Change in, can you just write the equations in the second one? The change in G equals change in G naught plus RT natural log of Q. Now, if we're at standard conditions, wouldn't all of our Q values be 1? All of our products we raised, they all be 1. 1 raised to whatever power. It doesn't matter what reaction we have. Wouldn't we be taking the natural log of 1, which is 0? If it's a natural log of 0, and we're at standard conditions, it kind of, the formula just reminds us that change in G would be change in G naught. Okay? But where this equation really comes into play is if you look on the right-hand side. And I would really encourage you guys to walk through the practice problems of how they solve underneath in this page. But can you guys look on the right-hand side where it says change in G equals change in G plus RT natural log of Q. And here's what I want you to do. Would you acknowledge that if I'm at equilibrium, my reaction is not spontaneous. At equilibrium, change in G equals 0. So what I want to do is I just want to show you something really quickly. So our change in G, can you write underneath change in G, can you write 0? And if we're at equilibrium, it's not keep the rest of the equation the same, equals change in G naught plus RT. But if we're at equilibrium, we're no longer having a Q. Wouldn't it be natural log of K? Are you with me? Now watch. If you rearrange the equation, you will get change in G naught. And this is the equation I was talking to you guys about earlier today. You write change in G naught is equal to negative RT natural log K. Boom, goes the dynamite. That right there, can you underline with a different color the change in G and the K? That is the equation that relates Gibbs free energy or thermodynamics with equilibrium. They love giving you problems where they give you the constant of K and ask you to solve for G, or giving you the Gibbs free energy and ask you to solve for K. The more practical equation, though, is, can you write the one right underneath that? K is equal to E. K is equal to the E as in the little e that when you're getting rid of a natural log.
Oh.
Is E raised to the negative change in G over RT. Let's make sure that's like, can you put like on a diagonal or just so we know that it's being divided by. Okay, that is how we solve for the K when we want to. So that's rearranging. Now, if we want to solve for G, do you realize we can just plug in the K, right? Natural log of the K, plug it in, right? If we are solving for K, that's the rearrangement. We essentially, if you guys don't know what we did there, we essentially took E to the power of both sides. And that's how we isolated K by itself. You have to divide on this. Yeah. I would really encourage you to memorize those two equations. Why? Because you do not want to have to be deriving it from the change in G equals change in G naught equation above. At least I wouldn't. No. You would, this would be, you know how I envision this problem? This could be part of the first problem on the test is always an equilibrium problem. So couldn't they give you a whole thing where you solve for the equilibrium constant? Yeah. They give you initial amounts, whatever else, and they solve for the K. And then halfway through the problem, they're like, hey, let's switch this over to thermodynamics, and they ask you to solve for Gibbs free energy. And that's where we use that equation.
So we do or do not?
You will not get those equations on the file. Oh, we can take a look at it. They might give you no, they won't. No, they won't. They won't give you either of those two. They'll give you the upper equation, that one, and they'll expect that you'll be able to derive it by putting 0 and natural log of K in there, but they will not give you those two equations, which is why students that don't memorize those two or don't know in advance, they get butchered when they hit a question that asks them to solve for K given G because they have no idea what equation to use. Can we lock that into our brains is something that's really, really important. Yes. Yes. In fact, for the sheet I've been giving you, And in fact, what I'll do is I'll print out the newest one from the 2007. You can actually look online, but actually don't do that because I don't want you to accidentally see. By the way, your final exam is not going to be one of the actual years. It's an unreleased thing, but I want you guys to be able to practice on released exams. Please don't look at anything from like 2014, 15, 16, 17. Don't look at any of those online because I want to give you those as practice. I was after probably there's 2010 and a few other ones as well, but yeah, I don't believe we have that, but I can verify. Okay, now.
Wait, so in class, we didn't really use the change in G in class, but that above equation looks familiar.
Which one?
Like the change in G equals change in G naught plus RT ln Q.
You know why that looks really familiar?
G, right?
Yeah. So can you write next to it? Can you write to the right hand side? Can you write E naught, or E is equal to E naught. Does remember what Nernst's equation is?
Oh, this is the next equation.
Is it plus or minus? I feel it's
I think
it's minus RT natural log of Q.
Yeah.
What is the Nernst
That's the Nernst equation.
equation do?
That allows us to figure out what the voltage is when we're not at standard conditions.
Oh, is it RT? I think it's 0.05.
Oh, that's right. It would be RT over N, whatever. So let's yeah. So can you guys?
Divided by something.
N over what's the other thing? Okay,
Yeah, over
F.
that's right.
F and F, yeah.
Oh, yeah, and F, yeah.
Okay, so this is me not being very sharp right now, but you're right. If it's at a regular temperature, then we would just have the 0.0591 and we have log of Q. But essentially, they're essentially how we derive there's the same derivative of how we got these equations. Okay, any questions on what we've just talked about here? The one thing I've not talked about here is Q equals MCAT. Briefly, but do you guys understand how Q equals MCAT works? Okay, so
I'm not really sure.
watch. I'm going to switch over to my screen here. Can you guys, do you guys have computers or no? Okay, can you look on with someone else really quickly on the computer? And if you, I'm going to put on.
So where we going? This is so wrong.
I just hope it's fine.
I'm going to give you my, right now I'm sending you guys all the link of the Google Hangout. Go to the Google Hangout, please. I just sent it to you. Okay, join me, please.
Join me. I mean, if you're starting, go for it. Wait. I want to join so we get a good view of this.
Emojis.
I'm sharing you right now. All right. Is everyone able to see this right now? I don't have you on, James. Okay, I'm going to briefly talk to you about a heating curve, and then I'm going to do a Q equals MCAT problem with you, and that's going to be the end of the lecturing portion because, again, now we're going to go back to the Medicina para Bravos because this is not the most exciting stuff. But I want you to look on the, can you guys all see the screen right now? Okay, Q equals MC change in T. That Q should typically is a small q, but that is heat lost or heat gained. So anytime we have a change in temperature of something, we can solve for the heat lost or gained by multiplying the mass by the specific heat of that particular material. So every single material, every single substance has, you might want to mute yourself. Every single substance has its own unique C. Now, I want to point you out to this graph right here. And this is a graph of water changing temperatures. So anytime we have a change in temperature, so the temperature here is going up. So if we have ice, an ice cube, let's say the ice cube is at minus 25 to start off with, right? If we go from minus 25 to 0, at all times there, isn't the temperature increasing? So if we look at our formula for the temperature increasing, we're going to be able to plug in the mass of the ice cube and the specific heat of ice, and we'll be able to figure out how much heat it took to go from minus 25 up to 0. Are you with me? Time is as the reaction goes on, right? So that's why we don't go straight up. Now, here's the problem. When we go from an ice cube to a liquid, when we hit 0, 0 is the equilibrium point between a liquid and a solid. So if I have an ice cube at 0, it can exist indefinitely as both ice and water. Are you aware of this here? Now, if I keep on putting heat in, what'll happen is that the solid intermolecular attractions will get loosened and weakened as I put more heat in. But the temperature will not change until all of the ice has become a liquid. So if you take a look at the formula, in order to figure out the change in heat, there is no temperature change involved when we are actually changing the state of something. So see how at 0 degrees Celsius, the solid just stays as a solid until it completely dissolves. So here's where it hits the 0 mark. We keep on heating, and as we heat, all the intermolecular forces are being broken in the solid until we hit right here, and now all the solid is gone, and we are now a liquid, and only then can we start raising the temperature again. Are you with me? Now, why is that important? Well, because the formula, whenever we're at a change of state, is different because we have to use, instead of Q equals MCAT, we use Q equals M times either the heat of fusion or heat of vaporization. Now, just so you're aware of this here, and I'm hoping this is vaguely tickling the back of your brain when we did this originally. If it's not, then we need to do this right now because it's entirely likely they could give us a Q equals MCAT problem. Isn't Q heat? Couldn't they start us off with a Q problem and then morph that into an enthalpy problem? And then all of a sudden we're in a thermodynamics problem. So we have to be able to use Q. So couldn't they give us the mass, the change in the C, and the change in temperature? And couldn't that allow us to figure out the change in Q or our Q? And then couldn't they use the Q to solve enthalpy or make that enthalpy and then work for the rest of the problem? So watch. Mathematically, every single solid or liquid has a specific heat of fusion and a heat of vaporization. Heat of fusion is the amount of energy that's required per gram of something to change its state. So do you see how the heat of fusion, which is to change it from a liquid to a solid or a solid to liquid, it requires, and they use calories because evidently we're in old school here. It requires 80 calories in our world. Wouldn't it be joules? And there's 4.84 joules per calorie. So they could have in this problem done 320 something joules per gram, right? But 80 calories per gram. That means that if I have 10 grams of ice, wouldn't it require 800 calories of heat to actually melt all that ice to get it to a liquid form? You guys see how that works? So anytime you see a heating curve, every time we have to break intermolecular attractions, we're going to use the Q equals ML. That L is either heat of fusion or heat of vaporization. And if you're wondering, think of fusion, isn't something fusion forming a solid? And vaporization, isn't it forming a gas, vaporizing? Gas to liquid or liquid to gas, we use the heat of vaporization. If it's going from a solid to a liquid or a liquid to a solid, we use the heat of fusion. Because the reality is it's fusing when it's going from a liquid to a gas, but it's not fusing when it's going the other direction. It affects the sign because if we're going one direction, our change in energy will be negative, and if we're going the other direction. So if we're trying to cause something to go from a solid to, let's picture this for a second. If we want to go from a liquid to a solid, right? Liquid's at a higher temperature, right? When we get to the point where we want to make it go into a solid, mustn't we lose even more energy from that to get it to actually form the solid? Because doesn't ice have less energy than a liquid does? So you have to be wary that the sign in front of the Q will be different if you're going up or you're going down. If I'm going up, I'm going to have a positive Q. If I'm going down, this space right here is going to be negative Q. This line right here is going to be negative Q if I'm going down. If I'm going up, it's going to be positive Q and positive Q. What I've seen students do is this. You know, if anytime we change the temperature, we use Q equals MCAT. So Q equals MCAT here, Q equals MCAT here, Q equals MCAT here, right? If we're going down, wouldn't we have Q equals MCAT, Q equals MCAT, and Q equals MCAT? But wouldn't the change in temperature be negative each time? If my change in temperature is negative each time, what's going to happen to my Q? Wouldn't it be a negative Q? So we have negative Q, negative Q, negative Q. Well, then they forget for the Q equals ML because there's no temperature change. They forget that we're actually losing energy along the way here. So they go negative Q and then they write positive Q and it cancels out what they've done and they get the problems wrong. So anytime, can you make this general statement? Anytime that you are moving down a heating curve, all of the heats are negative. All of them are negative. True story? Okay. Now, last thing here. Can you? I'm going to turn back over to you on the board, and then from here on out, we're going to be working on practice problems. Well, I'm sorry. I don't think we're going to put the practice problem in the video because there's going to be so much downtime in between. I'm going to stop sharing, and I'm going to go back to you. Okay, so Mary Catherine, you are now have control on the board. This is the last thing. You guys have borne with me really well. I'm stopping screen sharing. There we go. So can you, in the middle of the board, can you write heat lost equals heat gained? Right. That's how, yeah, it's how, just right. Actually, write the words heat lost equals heat gained. Holy cow, I just lectured for an hour and a half.
That's a long lecture. Yeah.
Wow, you guys are really hanging in there. Sorry. What's that? Oh, yeah, with the claws. I thought you were being incredibly morbid. I thought, what sort of a horrible human being are you that wants to show a cat hanging? That's what, yeah. Okay.
I said hang from a tree. Yeah, exactly.
Yeah.
For a second, I was like, I think we need to have some help. He needs hugs.
Cody needs hugs.
All right.
It's true.
Last thing. You guys have been champs. Okay. So watch. Heat lost. That's after you mentioned it, I realized that at first time I thought, and
Oh, you mean like, oh gosh, like a cat hanging from a tree. Like, not like the dead boy.
Not yet. That's after. But then it's got way more life.
So when we said hang in there, that's what I was talking about. I mean, I was like hanging cat.
Why am I the only one?
okay, last teaching concept. So one of the things they love, and this is actually called calorimetry. Calorimetry.
Oh, is this the section that was in possible?
We did a lab, right, on the calorimetry, if I'm not mistaken.
I hated that so much.
Okay, so let's just get that recorded for future. So when I look back later on, I'm like, hey, how did that go? All right, so watch. Calorimetry, all it is you take one item that has a particular temperature and you put it in with another item that has a different temperature, and the temperatures equal each other off. Now, typically what we do in that case, and what we do in that case is we almost always put it into a container that doesn't allow heat to be gained or lost. So let's do this for me. Would you agree with me that heat is Q? So can you write erase whatever you just did there? I appreciate the initiative, but let's just write this. Can you write negative Q, negative baby Q, equals positive baby Q?
Do you have any big cube? Yeah.
Honestly, it's really weird because I've always used when I did Q equals MCAT, I always did baby Q equals MC change in T, but sometimes you see it as capital Q equals MC change in T. I like using baby Q because that heat is the same heat that we used. Remember at the very beginning we talked about the internal energy is equal to heat plus work, Q plus W. That's this Q right here, heat lost or heat gained. Now, let's go on side farther. Can you on the side write next to heat loss, can you write Q equals MC change in T? Just up there, just so we know what the Q equation is. Q equals MC change in T. Okay. Now, what we can do is this. Whenever we have heat loss is equal to heat gained, we're going to have two different substances. So what we're going to do is we're going to write MC change in T on the left-hand side. Equals MC change in T on the right-hand side. And you can put like parentheses around the whole thing on the left-hand side and write negative. I think you want to put an equal between the two of them.
Is it like negative MC change in T?
There you
So watch. Here, I want to do this. I don't want to go through an entire problem, but I would like you guys to try a problem like this so it's not surprising for you, because I feel like we're due for one of these types of problems on the AP exam. What we have here is this. Let's pretend that we have, can you draw a little beaker to the right-hand side? A little beaker. And put water in the beaker.
Should it be bigger?
No, that's perfect. Okay. And then can you write, put a little arrow and write 60 degrees Celsius in the actual water, not in the. And actually, let's make it lower. So erase that and let's put an arrow to the actual water. And can you write 20 degrees Celsius? Okay. And then we're going to draw like a, you know how you draw like a nut, like for a screw and a nut that goes around it, like a hexagon. Okay, draw a circle above it. Draw a circle above. Draw a circle above. This big. It's a little tiny circle like this.
You want like a
Okay, and put an arrow going towards the inside. And can you write an arrow towards the circle saying 800 degrees Celsius from the side? 800 degrees Celsius. And can you write copper? Okay, so you're saying you don't remember this, or you do remember this?
I remember doing it.
Okay, now hey, focus. Next, like literally for 3-4 minutes, we're done. So what we have going on here is we have a piece of copper that's at 800 degrees Celsius, and we're dropping it into water at 20 degrees Celsius. Tell me what's going to happen.
They're gonna cancel each other out.
Really? Perfectly. They're going to perfectly cancel each other out. Well, let me just hold on. Let me make some generalizations. Will the copper, when we throw it in the water, will the copper maintain its temperature of 800 degrees? What'll happen to it? It'll go down. Will the water's temperature of 20 degrees, will anything happen to it?
Yes.
It's going to go up, right? Now watch. It really depends on a couple things. Doesn't it depend on how much water we have and how much copper we have? But ultimately, will you agree with me that the final temperature between the water and the copper, they're going to stabilize at an equal temperature? Will you agree? So what we can do in this case here is this. If we look at the MC change in T and the MC change in T, won't the copper be, could you write Q cop, right? Subscript of cop next to the Q, the negative Q, right? Right, cop there. And can you write H2O next to the water? As a subscript, I'm sorry, H2O next to the Q there. Would you agree with me that the copper is going to lose heat and the water is going to pick up the heat? So since that's the case, the mass is going to be the mass of the copper on the left-hand side, right? Won't the C be the specific heat of the copper? That's not going to be the same specific heat as the specific heat of the water, nor will the mass be the same. Agree? But what we do know is this. Can you write change in, underneath the change in temperature, can you write temperature final minus temperature initial? And underneath the temperature, the change in temperature on the other side, can you write change in temperature final minus temperature initial? And can you circle both temperature finals? They will be the same. So what they will often do in a problem is this. They'll ask you, they'll give you all the information, and they'll say, what is the final temperature after these two things have been combined? Now, we'll have to know the mass of both. Would you agree? We'll have to know the specific heats of both. And then we have to know the initial temperatures of both. And then can't we isolate the final temperature on both sides and combine them? Absolutely. In fact, one of the things they will do often is, now, in any problem, when they give you variables, don't they have to give you all but one to solve? Now, in this case, it looks like two, but isn't it?
Do you write this out as
Plug it.
you plug in and
And instead of the initial, you write 800.
what do you put?
The specific heat, you have to look at a table. They have to give you the specific heat for copper.
Wait, so if all you give you is initial temperature, right?
They have to give you more of that. If they gave you initial temperature, they'd have to give you the mass of both things. If you look at all the variables here, you put your finger on the mass.
Yeah, so all you have to do is find.
No, okay, watch. I'm glad you brought that up. In this case, does it matter if we're in Celsius or in Kelvin? No, because the change in temperature, the degrees is going to be the same change in Kelvin or change in temperature. So if you wanted to change that to Kelvin, we're just going to get a Kelvin temperature is going to be exactly the same ratio. So if you're like, want to be standard all the way across, keep it in Kelvin, but you don't have to. It's an extra step. But I almost feel like I want to do a full problem out on this. But can I urge you, particularly you, look through this packet here, because they do a heat loss equals heat gain problem. See how they rearrange a problem to isolate a variable and solve. But that is a problem that I feel like they're due to give us in soon. Okay, any questions on this? Takeaways. The two formulas, can you slide the screen a little bit towards the right? Those two formulas that relate Q and or K and G are incredibly important. There is one more formula. Can you write change in G equals negative NFE? Incredibly, this is the third in the trilogy of incredibly important problems. Can you write NF and then change in G naught equals negative NF E naught? And the E is one of those cursive, you know, the cursive E that we use.
Okay, what is the thing? This is so stupid. What is the thing at the top, the very top reaction? That curve.
That's the sum.
That's supposed to be the sum.
The sigma.
It's sigma. It's sigma. And it actually should be like square, a straight line on the top. James. There actually should be a line on the top and bending down. No, I'm terrible at this, but I'll do it down briefly.
Can you use it to do the probability?
So on this right here, they actually, when you do it, it's actually this deal right here, and it's actually a little sum of.
It's okay, we tried, we did good.
Now, this right here, pause. You underline these two right here. This is the one connector between electrochemistry and Gibbs free energy. That's incredibly important. And you know what? They haven't done that recently, but they're that evil that I could see them doing a problem where they force you to go to use those three equations. Why not? I have seen this though. I have seen them start off and give you like a cell to work with, and then then they've had you switch over to Gibbs free energy.
Wait, this one up here is for it gives to what?
Equilibrium.
First test. I feel like I would get lost. They give me a bunch of stuff, and I'd be like what?
And that's why honestly, over the next 3-4 weeks, so I think we still have 4 weeks before the AP exam. Especially the last 2 weeks, where I'm gonna give you guys literally, I'm gonna give you a problem that has the mixtures of like the new format, and your job is to weed through and specifically isolate, because every question, if you know what the formulas are you're using, they're easy to solve. It's figuring out what the heck equation you're gonna use. Now let me revisit this equation right here. Change in G equals negative NFE. F is Faraday's constant. Remember the 96,485 coulomb per mole
Yes.
of electrons? N is the number of moles of electrons, which means that you have to be given a problem where electrons are being transferred from one thing to another. And remember how we do the 2 half reactions? If one half reaction is 3 electrons being spit out and the other one is 2 electrons being grabbed, 6 is our N.
Yeah, I get that, but what was that?
So if you ever want to go between thermodynamics, G and G, and electrochemistry, E, that's the formula that we're going to use.
Yeah.
E naught, by the way, wouldn't we use that? Wouldn't we get that from the voltages from
from
equation? Yeah. So those equations right there are the incredible important ones. All right. That is the end of lecture. Come here, Catherine. Thank you so much for helping us with that. And cut.